Thank you very much. My name is Roger Roots. I'm with a company called Experior Laboratories. In the agenda it says it's about chalk testing methods. That was my colleague's presentation, who's not here, so I changed it up a bit, and I'll be talking about vibration testing of large, extra large payloads, and hopefully hope you find it interesting. So anyway, just to give you a quick brief, Experior Laboratories, we're a Southern California-based general environmental test laboratory. Do many things, anything you can find in the middle standard A10, DO 160 type of standard. In the early days, got started almost 20 years ago, so we'll celebrate 20 years next year. We got started coming out of the fiber optic telecom market. You should test very small components. Over the last 20 years, our scope of testing has widened, and with that, our test articles that we see at our laboratory, they have widened and they have grown. So initially, when we got started 20 years ago, connectors, cables, cable assemblies for various applications been our go-to products that we've seen. So fairly small products, connectors and all the things that interconnect and power systems that are out there. Been a government-approved test laboratory with the Defense Logistic Agency, NASA-approved test laboratory for both Orion and SLS, but always within very smaller components, 10, 15 pounds type of components. Something you can mount very easily on a single plate or on a cube. I think I have a pointer here. On a cube, something like that you manufacture a plate for, or just make a plate that you mount directly to an armature, a fixture you mount directly to an armature. And again, this shows you a shaker armature that is usually about 1 to 2 feet. Some of our bigger shakers are 40,000 pound force shakers, have about a 3-foot armature. As you need to expand your test surface because your test articles are growing, in the vertical axis you can use something that's called a head expander. It's basically a platform that attaches to the armature of the shaker, basically a turned around pyramid, and that will give you a square surface to work with. In our case, we have head expanders anywhere from 36 inches to 72 inch in diameter. And again, that's if you have test articles that keep you within that area, that platform, that kind of footprint. But what if things grow, right? What if things get larger? So, in this case, we had a test article that we, off the shaker, supported with a static stand, just a test fixture. We had this air duct here, and obviously this is the test article. We tested it on the slip table, but here also on the head expander. So we can use off-shaker support in order to accommodate larger test articles. What you can also do is, and we do quite regularly and have another campaign starting next week, you can tandem up 2 shakers, what we call that a dual shaker application, where you actually drive 2 independent amplifiers, 2 independent shakers from the same controller. And with that, you have a spanner, you have, you can have a spanner plate, so you line them up very precisely with a laser tracking system that we have, and you have a spanner plate that you bolt down across both shakers, basically tie them together, so they become one. The same thing on the head expanders. You move the shakers, and we have a floor. You can see these rails here in the floor. We can move the shakers anywhere on that isolated floor, bring them very close together. The head expanders almost touch each other, have a spanner plate go across, and make one test system, one test platform out of 2 systems. Here in the back, you see a larger fixture. This is an 8 by 24 foot fixture that we built, and that fixture alone weighs 3,500 pounds. And then the test article that goes on top of it, which I can't show you, is another 2,000 pounds. So you end up with a 5,000 pound payload on 2 shakers, something that for some space flight hardware. Then a new challenge came along for even a bigger test article, a test system. So we had a company called Astrobotic approach us to structurally test or vibration test their lunar lander, which is part of the Commercial Lunar Payload Services CLPS NASA program. Now, in this particular case, we're talking about a structure that is 12 by 12 feet wide, about 10 feet tall, weighing approximately 13,000 pounds. So before we had payloads about 5,000 pounds, now we had a challenge of a 13,000 pound payload that totally outgrows a vibration system. So how are we going to do that? So our team here, so you can kind of see the size, correct? So if I stand next to the shaker, 6 feet ends up about here. You can tell where this goes. So we were contracted to acoustically test that structure. So that's here where we set up speakers. We're not talking about that today. But again, we acoustically tested that structure, basically blasted sound waves at it. And then we sine vibration tested it on our vibration system, both in the X and Y lateral axis, as well as in the vertical axis. So the challenges with large, tall, and heavy payloads are overturning moments. When we have, think of just a block of metal, something that's very close to the surface of the shaker, very low center of gravity, you have no overturning moments. You can use a regular oil film based slip table. But when you have a test article where the center of gravity is way above the shaker, you're dealing with overturning moments, at which point a regular oil film slip table will no longer do the job. So for the X and Y axis, what we did is we contacted the Team Corporation. They're out here on the floor as well. And we purchased one of their T-film bearing slip tables. And they can tell you all about it. But a T-film bearing slip table has very good overturning capability. Also, because of its design, and again, Team Corporation can explain that much better than I can, it also accommodates much higher payloads. So for X and Y, we employed this tool together with an on-the-hole sticky T4000, which is a 40,000 pound full shaker. For the Z-axis, you kind of fight in the same thing. So you have heavier payloads where the mass is much further off the shaker. So if you just have a cube fixture, as I showed you in one of the first slides, and you mount it directly to the armature, your payload is very centered on the shaker. But now we have a 13,000 payload that's distributed across 12 by 12 feet. So a lot of the weight is hanging out on the shaker. How are you going to keep that stable as you vertically vibrate it, correct? Because you don't want it to tip it sideways. So you fight overturning moments, and you fight crosstalk acceleration. Overturning moments can overpower the bearings of the shaker itself, because inside the shaker, where the armature moves up and down, there are supports in there. There's auto-centering features and airbags in there, but because of the heavy load, oversized heavy payload, you have to do additional things in order to keep that structure moving straight and not tip. Tipping be dangerous for everything, including the shaker itself. So what we employ, or what you need to use, or what's out there, is you need to make your setup, your vertical setup, stiffer. You have to make it more supportive and give it less room to move sideways and keep it in this vertical direction. So you employ a tool which we call a guided head expander. And a guided head expander has a couple of things. So it has bearings that provide additional motion direction, additional stiffness that helps you keep that payload vertical and moving in that same direction. what we had to do, because now we're dealing with a 13,000 pound payload, we took a standard head expander and we kind of put the Experior Laboratories twist on it, modified it a bit. What we had to do is our engineering team, designed some custom aluminum roller flexure bearings, as you can see down here, that we mounted all around the base of the guided head expander, and that provides some additional support and advantage. So first of all, it restrains motion in a vertical direction. It gives you more lateral stiffness. It provides more vertical stiffness. And because your test article or the test itself will run for a while, there is some heat that you have to accommodate for too. So we had to pick some heat and fatigue resistant aluminum to manufacture these bearings with. So for the load, what we had to do, and you see that later in a video where they are, we had some, not custom airbags, but some specifically selected airbag isolators that we placed around the head expander in order to absorb the weight. And also to keep the natural frequency of the shock absorbers below the test frequency that the test article was tested. So now if the video will play, let's see if it so you can see all these bearings that we mounted. I actually have 20. So you see all these bearings that are mounted all around the base of the head expander. And then you see the airbags in there that give us additional support to absorb weight. Now what we proof loaded it with here, this is obviously not the lunar lander, but what we proof loaded it with is one of our 72 by 72 inch head expander, which this one weighed 17,000 pounds. So our target was 13,000 pounds. We proof loaded our solution with a 17,000 pound slip table, and we got the thumbs up. So it worked fine, and then I'll go back a couple of slides and show you how this. So this is how then it looked again with the lunar lander structural test model up on top of it. So again, you can just see the pure size of that thing. This huge 40,000 pound force shaker down below, which is 8 foot to the top of the head expander, looks fairly small compared to what you have on top. And you need to keep that all stable as you run it through your, and this was just a sine vibration test, not a random profile, but just a sine vibration test to run that structure through to make sure that, again, this structural test model here of a lunar lander we hope to see back when it's like the actual flight hardware in 2 years when it goes up. Hope to see that back. That's it.